116 teragrams of methane per year. Although most of the mitigation will focus on anthropogenic methane, what we can't ignore is that what we're actually trying to do is to reduce the atmospheric methane by 400 parts per billion, which means that we have to really pay attention to what's happening in natural systems, whether we intend to mitigate that methane or not, and update targets effectively. And so when we look at natural emissions, studies are suggesting that those emissions are increasing, and it's mostly focused on the research that's being done in wetland ecosystems. And so we believe that natural emissions are increasing with temperature, which of course isn't surprising. To do this work, depending on the community that you're in, you will approach trying to understand global methane dynamics in a number of different ways. If you are in the atmospheric sciences, you might be more interested in top-down approaches where they are really focused on understanding changes in the atmosphere and then using information from bottom-up approaches to then distribute the amount of change you see in the atmosphere to certain source categories. Remote sensing uses information about spectral reflectance, trying to estimate total column methane changes, and has been more recently used to detect plumes or point sources that might exist in the landscape to identify sources of methane that we may not have previously had a way of quantifying. But bottom-up approaches, that's where we fall. And so that's where measurements are being made from particular point sources, and we can use that to understand flux rates, how they're associated with temperature and other processes to then upscale and understand when to understand what's happening in terms of natural methane emissions, the best way of understanding that at the ecosystem scale is by the information that this community provides. And so the data that is being collected from this community will not only be used, of course, by us, it will also be used by process-based modelers who are then taking in this information in order to understand what's happening at the surface. And so the model I showed before on the projections or estimates of what's happening in natural wetlands, this is based off of a process-based model that also relies on flux information that is collected on point sources. We have FluxNet Methane, which is this amazing community-driven product where methane data has been collected from individual principal investigators. It's been standardized by an amazing group of people and made available to the wider community. This information is now being utilized in both process-based models, and it's being utilized by the atmospheric community to understand how changes at the surface are influencing what's happening in the atmosphere. But when you look at the distribution of these towers, you do recognize that if you were designing a study to make global estimates of natural methane emissions, I don't think you would do this. And it's clearly it wasn't the intention of all these individual PIs operating independently to support this type of research, but the world is relying on this research. And so we have to be aware of that when we're thinking about what we need to do next, where there needs to be towers. You will also notice by looking at the list of vegetation types that a lot of these categories would fall into wetland ecosystems. And so we have to recognize when we use this data, what that will mean and what kind of biases we might be putting into models if this is the data set that we're relying on. And so today, I'm going to show you a little bit of information about my goals to look at natural methane emissions and how much methane is being emitted by natural systems and how that could be changing over time. And so to do this, I use that FluxNet data product. I first started out by figuring out if my overall goal is to understand natural methane emissions and I decide to focus on the US first, um, can I use towers within the United States to make these type of estimates? And so first I had to figure out how representative the towers are within the United States to every other location that exists in the United States to figure out if it's even possible. And so to do this, I did a multi-dimensional scaling of information about climate, about spectral information on vegetation and vegetation type to figure out how many different clusters would exist within the US and then how representative are towers to those clusters. And so if you look at the black lines, they're showing you the space that is available in terms of the types of dissimilarity that exists across the 10 clusters in the United States. And if you look at the color bars next to them, they indicate the coverage of that representativeness for different tower categories. And so I broke the towers up into towers that are measuring methane and reporting it to FluxNet data. And so this is information that is available to the wider community, by towers that are measuring methane regardless of reporting data, and then by neon towers so that we would know if we have the capacity to put estimates of methane emissions on neon towers, what would that do to our ability to upscale this type of information? And by using towers just within the US, we were able to see that tower representativeness was relatively low for most clusters. And the only clusters where the representativeness seemed somewhat reasonable were in the Eastern United States. But if you take into consideration vegetation class, there isn't enough towers distributed across vegetation class to make you confident that we could actually scale the data across these vegetation classes. And so in order to do this type of work, I definitely have to start with a global data set, whether that is appropriate or not. It's where I got to go. And so I took all the information from the global data set. I made monthly estimates of methane fluxes from the different ecosystems. I used information on vegetation type, climate, enhanced vegetation index, and NDVI from MODIS, and the climate information that was measured at each site. And I made two versions of a model, one that included vegetation class and all the climate and spectral conditions, and another model that only included climate and spectral conditions. I used a random forest machine learning approach, and then some validation to understand how terrible my model is. And so in order to do this and project it out into space to come up with a total budget, I also have to ensure that my climate data is available spatially. And so I use the Terra gridded climate data, and of course, the same MODIS data that I used for the individual tower models. And so together, it wasn't surprising that with this data set, temperature and vapor pressure deficit were the most important predictors of monthly methane emissions. And when I dig a little bit deeper to see how well those models perform for different vegetation classes, it's also not surprising that I don't do a very good job for a number of classes where we don't really have enough towers, even with the global data set, to make estimates for those vegetation classes. And so the models represent some vegetation classes much better than others. And the towers, even when I look at the climate space within the US, the climate space that's covered by the towers and those data sets, it's not fully covered within the United States. So I'm extrapolating across vegetation classes that I don't have information for. And I'm also extrapolating across climate space, but that doesn't stop me. I still make my estimate. And so in 2020, emissions for natural areas are about 3.9 teragrams, plus or minus 1 teragram of carbon. And a lot of those emissions are coming from grasslands, just because grasslands are the largest category. But when I look at my model, I know it really sucks. And it sucks for a number of reasons. One being that it clearly is showing that a hot spot for methane production is in the Southwest, and that is not the case. And so my model is really being driven by temperature. Not surprising, but it's less driven by moisture conditions because most of the towers are wetlands. And so temperature comes out to be the dominant driver and will make my predictions extra terrible in warm places, even though that's where I really need my model to work well. When I compare my model to the 17 biogeochemical models that are also being used to make statements like wetland emissions are increasing and we should be terrified, my model, even though it's terrible and overestimating, comes in at the bottom of the projections that are made for the United States for the process-based models, suggesting that we all have quite a bit of work to do, because if I'm overestimating and at the bottom, then we're all kind of in trouble. To get a little bit deeper into why my model is so terrible, even though I know, I compared my model estimates to the terrestrial ecosystem model, which is also at the top of the projections here. And this model has some static and dynamic parts, but the most important part is that we're all using different climate information, we're using different land cover information, and so some of those things are going to be responsible for these differences. When I look at the vegetation cover that I'm using, if I switch to using the terrestrial ecosystem models vegetation, I can that's responsible for about 28% of the difference, but climate is less than 10%. And so we all have a lot of work to do in terms of what layers are best to predict and upscale methane. There needs to be a lot more development. And clearly, there needs to be much more representative information from the towers. But part of that is because our community is going to put infrastructure in places where we know and expect there to be fluxes. And so we're out there chasing fluxes, but if the global community is using these data sets to drive models, we are putting biases in our data sets and in theirs because we're just chasing fluxes and we're not collecting information that's more representative of all the systems that don't produce as much methane, but that's also a limitation of the equipment. When we think about where we need to go in the future, knowing that it's unlikely that we're going to get so much money and support and grow our community so quickly that we're going to have a bunch more towers, that's unlikely. And so thinking about what we do have and what we can do with these different approaches and which approach is better at what level than others, we might be thinking towards focusing on data assimilation projects. How can we use flux measurements that are taken across scales and put that together to build up our data sets and work in some of the processes that we're missing? How can we develop layers that support scaling? And these same scaling layers would be important to work into process-based models. And so things like salinity have been brought up today, vegetation type, having better information about inundation fraction would be really helpful. Coming up with standards for testing and validating these data assimilation techniques will also be really important. We also need advancements in data model integration. So how can we work with the top-down community and build in new methods to integrate across inversion models and the bottom-up sources? How can we create the products that feed into the priors that go onto the inversion models, because they know how the atmosphere changed, but we know what the surface is doing, and building that gap will be really important. We also want to develop standards for uncertainty estimation so that we're all speaking the same language and we know what to expect from our estimates. One way that we're attempting to do this is by working with the existing infrastructure. And so NEON is measuring methane mole fraction at different tower heights across the US. And so thinking about how can we use this information and develop methods of estimating fluxes that are reliable and comparable to what we're measuring with the eddy covariance method. There are different ways that we can all work together to do this. We have to utilize the infrastructure of the entire research community. We want to think about how can we work with ESEL, the new synthesis center? How can we put in working group proposals to get some of this work done? We could also think about how to utilize NEON, putting in assignable assets proposals in order to get some of this data model comparison work done. We can think about utilizing the Yale Center for Natural Carbon Capture. They fund workshops and also postdoc positions in order to figure out what's going on with natural carbon emissions and also the potential for natural mitigation. We can also think about ways that we can support each other. organize information, data that's outside of the priority of AmeriFlux? How can we help each other out with collecting this information and creating products that we can share? And also, how can we help each other out to create opportunities to fill gaps in for other PIs who are doing all this work to provide data information that's way outside of their own research, that's really supporting the research of the entire community and other fields as well. We also want to think about what are our roles. Some of us are data producers and some of us are data users. And for those of us who are data users, there's less information about the standards that we need to be following so that the people who are doing the work to collect the data are getting efficient credit. And so we all have some homework that we need to do to make sure that we are supporting those community and really supporting each other. With that, I will take any questions and recognize all my collaborators. Can I take questions?
I'll start. I have a question, Sparkle. So earlier we recognized in the N2O and methane breakout group that there are different initiatives going around to synthesize and disaggregate chamber flux data, and we're putting those into separate databases. But maybe, do you have any thoughts on like kind of maybe organizing that better and coming up with more global? Because I think that would help fill in a lot of those gaps of places that have chamber data, but they don't have towers.
Yeah, I'm not sure that there's anything that we can do about the fact that people are going to utilize different repositories, which is great. Just put it in a repository. But having community efforts where we go and get all the data from those repositories and make a product that we would release, I think that might be a really good use of time and effort. And that being done, you know, every few years means that we'd have the opportunity to update it and provide the information to the models and data.
Thank you, Sparkle. So you were talking about the different variables that the model uses, and you mentioned that EVI and NDVI were part of it. I'm just curious how well they predicted results and what were the differences when you used EVI versus NDVI?
Yeah, so both predict really well. I was actually quite surprised when I was looking into what remote sensing products would help me with the upscaling, how well the vegetation indices worked. It was a little bit scary. They work pretty well, especially if you were doing some of the indices, you can get them on the daily basis. And those models were about 3 times better than attempting to use monthly information for monthly estimates. And so the vegetation classes work really well. It shouldn't be that surprising. I mean, there's a lot of plant-mediated methane transport. And so it's, I'm sure, directly related to that, but it works well. Both of them work very well, and using both of them in models is helpful. Although if you had to choose one, I would use EVI.
Sorry, can I just like a follow-up question? What repercussions does that have for scalability? Like, does that mean we can like go ahead and try to scale projects?
You definitely can, because the information is provided in spatial products with MODIS and with Sentinel. And so that, because it's available spatially, it wouldn't limit you in terms of trying to scale with that information.
Thank you.
Another question right here.
So you didn't use inundation depth or water table depth, but what were the barrier with implementing any kind of other surrogate hydrological variable, which?
Yeah, so it would be really helpful, right? Because essentially we're suggesting with these models that all wetland ecosystems are emitting the same rate, even though we know that if we're accounting for differences in water level, inundation depth, whether or not the wetland is actively inundated for certain parts of the year, our estimates would be much better than assuming some average wetland condition. But that's essentially where we are because we don't have very good dynamic information about inundation depth.
Hey, Sparkle. In my past life, I've been doing a lot of airborne adequate flux measurements, and oftentimes they're used to establish baselines for regional representativeness and whatnot. And I've been involved in a couple of campaigns that do methane adequate flux measurements. I was wondering, what do you see the potential for integrating some of those into your study here as well?
Yeah, so there's actually a Blue Flux project, which Sean is a part of, where we are working across scales in terms of flux information. There are individuals making chamber measurements, seeing what those estimates look like from stems compared to eddy covariance towers that are measuring methane at the ecosystem scale over mangrove and other wetland ecosystems. And then they're doing flights. And so on the days that they've been doing flights and doing the comparisons, it's also, I'm surprised at how well that information lines up across the chambers. We're all in the same order of magnitude in terms of the fluxes, but each approach that you use just has different limitations associated with how you make those measurements. The flight information is 1 or 2 days a season where they can collect information maybe at multiple times in a day, but the flux information will become really important for bridging gaps in between those different scales. And so really understanding how the different scales relate to the ecosystem level measurements will be key.
Hey, Sparkle. My question is, do you have a sense of how many towers might be making methane flux measurements, but have not yet shared those data to one of the regional networks?
There are a lot of them. I have a secret plan to engage with all of these tower PIs. And so it's really difficult when you are collecting information for your research. It's really difficult to allocate the time for a highly skilled technician to be processing this data and reporting it to AmeriFlux if your objective is to do it for your research. And so thinking a lot about what resources or benefits some of our labs have over others, I've been thinking about how can we provide data processing resources to individuals that might not have it on their own or who can't allocate the time to doing that and reporting the data. And so thinking a lot about how to create training so that we can train novice Flux data users to process data so that even within our labs, if we have the space or capacity, we might help out other researchers who might need that support so that we can facilitate more individuals reporting data into AmeriFlux and FluxNet so that that information is available for the wider community. But there are more than double the towers that are reporting data that can't report the data for different reasons.
Thank you so much, Sparkle. I think we're going to move on to our next talk. Okay, our next talk is from Stefan Metzger from NEON. Want to come up here?
Thanks for the introduction, Patty. Thanks for having me. Today I'm going to talk about carbon due, anchoring equitable climate solutions in directly measured greenhouse gas exchange. So some of the people in the impacts breakout today, they might have seen some of my spiel, but be assured there's going to be a couple of new slides in there. So really the motivation here is to link our flux measurement and make them relevant to help overcome some of the challenges that we're facing in our real world activities, such as emissions accounting. And one way how to create this linkage are market-based approaches. So you see two branches here. On the left-hand side, you have the creation of emissions, and some of them are going to be hard to abate. So there's going to be residual emissions. And at the bottom of that branch, that links to a market-based economy or carbon trade. Now, on the right-hand side, you have a branch that concerns itself with sequestration, and sequestration can be in nature, can be in ecosystems, but it also can be underground, in geology, for example. Through the transformation to credits, those link then again back to the left-hand side branch at the bottom into the carbon trade. Now, interestingly, both of these branches have its very own methodologies in how we count carbon and how we account for carbon. And so there's zero uniformity at this point, other than everybody uses the metric of a ton. But the question really arises, how many molecules of carbon are in your metric ton of carbon? And to actually make those interoperable, that's where we see a great example of where eddy currents can actually become relevant and help overcome some of these challenges. Now, to actually link, to bring the players together that are all part of this endeavor, we created the Carbon New Community of Practice about 1.5 years ago at this point. And the vision really is to bring direct measurements of greenhouse gas exchange in and out of the air, to make them useful to anchor fair and equitable climate solutions. And the mission is to accomplish that by bringing together stakeholders across the entire spectrum of climate tech. I'm not going to go through the entire diagram, but essentially from left to right as the center, you see we have our eddy currents measurements there. The idea is to even tap into the raw data to squeeze the last bit of information out of them and provide them in form of maps that are a lot more easily accessible and usable by some of the stakeholders that we're working with, and they provide 10 to 100 times information to then anchor, for example, remote sensing data or approaches like Sparkle was talking about. So getting 10 to 100x information out of those. For example, from a single tower, it's possible to get fluxes for 2, 3, 4 separate land covers once we disaggregate them into a plane. The idea is then the results are being locked in a blockchain, so they cannot be tampered with, and they're fully transparently available. And they're available both for public education, for your weather underground on your phone, so you can see what your backyard is sequestering essentially, as well as for carbon industry approaches and for regulatory accounting. So let's dive in a little bit into the AmeriFlux side of things. How can these unlock cross-realm climate solutions? So the beauty here is really that AmeriFlux, the essence of AmeriFlux is really simple. We count molecules that travel up or travel down, and that actually breaks down in a quadrant chart. And yes, obviously, when you look under the hood, there's uncertainties involved with it. Now, that said, when you look into some of the other current approaches in the individual carbon accounting sectors, there's oftentimes much larger uncertainties associated with those. So there's a lot of potential here that we can actually use. And now, interestingly, as one of the very few methods out there, eddy currents also allows us to work cross-sector. So yes, we can work already cross-sector in the nature-based climate solutions. We can work in ag, we can work in forests, but we're not confined to that. We can also work over cities, we can work over oil and gas, we can work over energy production and so forth. So there's not really any other methodology out there that's able to do that and account for ownership scale attribution and contributions to the climate, to the greenhouse gas budget. Now, how do we actually make these data more accessible and more powerful that we already have? So we go into the second part here, the flux mapping component. And yes, eddy currents can be very powerful, and the idea of it is fairly simple on the surface. Now, there's also a lot of limitations that come with it, and one is that every minute, every second, every hour, we're essentially representing a different mix of surface properties. Now, the idea here is that we can disentangle this type of puzzle by not mixing half-hourly information together, like what we've done for the last several decades, but we're actually using the changing source areas every subsecond to every minute to be able to map things out, have half-hourly maps, have tens of thousands of pixels for which you can now actually attribute emissions hotspots, emissions cold areas, and attribute that to different land covers, where you even get like intra-class flux variability that you can propagate as uncertainty, like we heard from Sparkle earlier. And so what the end result then looks like is a representation like this here. You still have the footprint that is kind of dancing around, but what you actually pass on in terms of an information layer that you can now marry with remote sensing or simply with your facility surveillance over oil and gas, for example, is actually the changing color map at the bottom. It's directly derived from the eddy flux measurements. So that's actually what's going on under the hood. We do a formal evaluation of the continuity equation. So that's where you see the colors changing in that little cube there on the right-hand side. And the nice thing really here is that from that point on, we are really able to integrate multiple different types of instrumentation into a single map or even into a single cube. We can work with towers, drones. We can then further tack onto remote sensing and propagate this entirety of statistical power that's really in our raw data, but that we're currently not fully tapping into. Here's an example how this can then look like in agriculture. Susie Wiesner published this recently. On the left-hand side, you see a traditional flux tower. And on the right-hand side, you see how it looks like when the information, the raw data information is actually mapped out. So you get this attribution to individual plot levels here. This is an oil and gas example. This was an unmanned flux aircraft measuring over a well site. And also here you can see, which is kind of in the center here, and you can see how the oil and gas methane emission can actually be contextualized with an entirely different sector where we have the majority of emissions, the red area in the northeast, which is methane emissions from wetlands in that case. So again, cross-sector. Now, a beautiful thing just has happened because eddy currents is typically it's complex. We talked about this. We can simplify it and create an interface that's more easily usable for the type of data that we have while carrying on additional statistical power. It's also becoming a lot cheaper. The annualized cost per kilometer square that we are characterizing with this type of approach is going down order of magnitude. So it becomes, it's achieving cost parity with some of the existing approaches out there, and it can help overcome some of the existing challenges. So overall, that allows us to integrate this chain in a maximum efficient way. And ultimately then link our two branches, the emissions branch and the sequestration branch in our carbon economy, through an integrated measurement reporting verification approach, essentially a benchmark that can be used. It doesn't have to be everywhere all the time, but so long as it coexists in several characteristic locations with existing sectorial carbon accounting approaches, one can identify to which degree an existing method might be biased or have tolerance. That resonates with you. Here's some examples. We're starting to work with the Syngenta group, for example, which is near real-time emissions mapping for some of the research and development side in agriculture. We're working with Black Swift for industry emission detection, geolocation, flux quantification. We've seen an example. And Margaret mentioned earlier, I believe it was yesterday, that between AmeriFlux and NEON, we're also thinking about sticking our heads together, integrating flux tower data, remote sensing data. And one idea would be to come up with open example maps for industry and regulation to kind of allow them to get a feel for the data and what it could do for them, and started this conversation there. We're also present at AGU, if that's of interest to you, if you're joining there, feel free to join our session. And some other kind of activities that we do, we're responding to federal requests for information, RFIs. So for example, greenhouse gas measurement and information system, there were 2 RFIs out recently. So we're trying to integrate responses across both academia, regulator, and industry fields and perspectives, and trying to bring that together comprehensively. So if that's of interest to you, carbondue.org, available to sign up. It's free for everybody to join. And with that, I'm open to take any questions.
Questions?
Hi, I was wondering if the code for how you created this time varying footprint maps was publicly available.
It will be end of January next year. So we have a grant that requires us to make that available. It's super messy right now.
Okay.
By that point, the intention is to have that cleaned up and make that more.
So this
accessible.
January or, okay, so this coming up January.
Exactly, January
Great.
24, yeah.
Cool.
Stefan, just one thing I didn't understand. When you said the measurement got cheaper, could you just elaborate on how that worked? I didn't understand it.
Yeah, it's cheaper in the sense per unit area that is characterized simultaneously. So you still have the startup cost that you need to get a tower out there. Once you have it running though, you can simultaneously characterize, for example, in more heterogeneous settings, you could simultaneously characterize multiple different land covers.
Thanks, great talk. I think it's readily apparent to me how this might work for like an oil and gas pipeline where you can see the emission, like you can see, it's very easy to see that point source of emission and use this method to find it and attribute it to the plant. But can you give an example of how it might work for something like carbon injection of CO2 into the ground for sequestration methods? Does it still work? Is that an application of this?
Yeah, great question. Thank you. So actually at Battelle, which is the entity that manages the NEON program, there's also a CCS program in parallel to NEON, so carbon capture and storage. And in particular for their permitting, they not only need to be concerned about what is going on, where is the CO2 bubble in the subterranean CO2 bubble, but they also need to come up with approaches how to quantify re-emissions. And so that is the idea where on the one hand, methodologies like this can track and trace and identify leaks that occur, for example, in pipelines, in transformer equipment, will not before the CO2 is actually injected into the ground, as well as re-emissions, and help separate that from the natural dynamics of CO2 interaction between the land cover and the atmosphere. Thanks.
Sorry, a quick one. Has this technology been used to verify projects with big certification agencies?
So some of the clients that we're starting to work with are interested in authoring these type of protocols. So Vera, for example, which is one of the certifiers, they currently do allow to use AmeriFlux measurements for quantifying co-emissions. So they essentially use soil cores to look at carbon in the ground in agriculture. Now, soil cores don't tell you a whole lot about nitrous oxide or methane. So that's where there is already an existing precedence where they do allow you to use eddy covariance. And so there's interest in the market to drill that open, recognizing that many of the existing technologies only see several puzzle pieces of the whole picture.
I can jump onto that too. I know in California, the American Carbon Registry, which is sort of like Vera, has used eddy covariance data for the carbon market there, but not carbon due in particular. Any other questions for Stefan? No? Okay, great. Thank you so much.
Thank you.
Okay, our next speaker is online, and it's going to be Eric Velasco from the Molina Center for Energy and the Environment.
Hello, I'm there. Hi, can you hear me? Hello? Hello? I'm there?
So we can hear you.
No, my microphone is on. Can you hear me?
Yes, we can hear you.
Okay, great. So let's begin. I'm very happy. It's great to be here with you at the AmeriFlux Annual Meeting, even though it is just virtually. I have a lot of material to share, so let's begin. During the next 15 minutes, my objective will be to demonstrate the potential of eddy covariant flux towers to improve air quality management and climate change mitigation in urban environments. Let's start explaining why urban flux towers can perfectly work as urban observatories. Complete assessments on air quality and climate need to explain the way cities interact with their atmospheres at different scales, including, of course, the local scale, which I call neighborhood scale. We have to look into the many physical and chemical processes going on within and above the urban canopy to improve the atmospheric environment. Among these processes is the exchange of energy and mass between the urban surface and overlying atmosphere. We have to do this through a combination of field observations and numerical modeling, including deterministic models and data-driven methodologies. Let's go to talk about the nuts and bolts of urban flux towers. Its proper use represents a direct assessment of the net exchange of energy and mass, including contributions from all emission sources and sinks from a footprint of a similar size of an entire neighborhood. To operate an urban flux tower, as any other flux tower, we need fast and accurate response sensors and an appropriate location. Topography must be flat, and the urban surface must be homogeneous, relatively homogeneous in terms of land use and urban morphology. Emission sources and sinks must be more or less well distributed around the flux tower. This is very important. Sensors must be mounted within the inertial sublayer, where turbulence is relatively homogeneous and gases, aerosols, and heat are well mixed. This layer is usually located at a height between 1.5 and 3 times the mean height of the roughness elements, I mean buildings and trees. A well-designed flux tower should be able to measure fluxes from a few hundred meters during daytime when atmospheric conditions are unstable, and up to 1 to 2 kilometers at nighttime when atmospheric conditions tends to be neutral in urban environments. By coincidence, these are the dimensions of the grid cells that we use to build emissions inventories by bottom-up approaches. The yellow squares in this figure correspond to the grid cells in the official emission inventory of key pollutants and greenhouse gases of Mexico City. Before moving forward, let me introduce the flux towers that we have operated in Mexico City and Singapore, with support of funding agencies from both countries as well as the United States. In Mexico City, we have operated 3 flux towers. The first 2 towers were part of 2 large air quality field campaigns in 2003 and 2006. The third flux tower was made possible after persuading local authorities on the need of measuring CO2 fluxes over a longer period of time. In addition to measuring fluxes of carbon dioxide, we have measured fluxes of energy, selected volatile organic compounds, and chemically resolved aerosols. In Singapore, together with students and researchers from the National University, we operated a flux tower in a low-rise neighborhood during 7 consecutive years. This has been so far the only flux tower in the tropics, in a tropical city. Its data has been highly appreciated by the international community. Now, let's talk about applications, starting with their application for measuring emissions of greenhouse gases and airborne pollutants. These are the CO2 fluxes that we measured in a busy residential neighborhood close to downtown. The urban surface always acted as a net emission source, and as expected, fluxes were higher on weekdays than on weekends, except on Friday nights and Saturdays and Sundays early mornings. Can you guess which was the reason? Well, the reason was the social life of the city, the party effect. The climate in Mexico is a kind of boring. It's quite constant throughout the year. So we didn't see a significant variability in the CO2 fluxes, except on December when schools close and some economic activities decrease due to Christmas holidays. During the pandemic, our colleagues in Europe were able to keep running 12 flux towers. The data collected by them has been very useful to evaluate the lockdown impact on anthropogenic emissions. At the time of the pandemic, our Flux Tower in Singapore was no longer in operation, but we had previously developed models to estimate emissions from each emission source. So by retrieving social mobility data from Google, Apple, and TomTom application, we were able to estimate the emissions reduction during the lockdown that in Singapore was called circuit breaker. During this period, emissions related to human breathing went up 29%, emissions from cooking activity 23%, but traffic emissions came down 38%. In total, we saw a reduction of 21% within the boundaries of this neighborhood. This is not bad. In fact, it's a great figure, but sadly, it was just a brief respite because CO2 emissions went back to previous levels after a few months. In Mexico City, we have used the Flux data to evaluate the accuracy of the gridded emissions inventory. In the case of CO2, we found a small overprediction in emission estimates due to errors in traffic counts across the student neighborhood. In terms of volatile organic compounds, species estimates, emission estimates of a species strongly associated with combustion sources were essentially correct, while emission estimates of a species such as toluene and benzene, which are associated with evaporative emissions, were somewhat overpredicted. In our second Flux Tower in Mexico, we used an aerosol mass spectrometer to measure fluxes of chemically resolved aerosols. For this particular sector of the city, we found that the urban canopy acted as a sink of nitrates, but as a net emission source of organic aerosols. Regarding sulfates, we observed non-flux, and this is consistent with the use of clean fuels in the city. Based on Munin-Obukov theory and challenging Reynolds analogy, we instrumented a bicycle and applied the aerodynamic resistant approach to map fluxes of carbon dioxide and moisture at high fine spatial resolution using as reference flux data from a tower that we had in the center of this neighborhood. According to our knowledge, these were the first maps at such fine spatial resolution derived from field measurements. We have also used flux towers to evaluate the role of urban greenery in the carbon cycle. What do you think on whether urban greenery can act as a carbon sink or as an emission source? Is this a myth or a fact? Our first approach was to compare measured fluxes against emission estimates obtained from activity data and emission factors. The difference between both was assigned to plant respiration at night and photosynthesis during daytime. But the use of emission factors and activity data brings uncertainties. So we decided to look into each individual component of urban vegetation. First, we evaluated the carbon removed by photosynthesis through biomass production in trees and turf grass. Then we evaluated the amount of carbon transferred below ground and lost by soil respiration. We also accounted for CO2 emissions associated with maintenance activities such as mowing. The only component that we haven't investigated yet are losses by leaching. Accounting for all contributions, we found that urban greenery in this particular neighborhood of Singapore is capable of offsetting up to 8% of all anthropogenic emissions. This is great, but this is only true under an ideal waste disposal management. If all gardening waste is burned, as in Singapore, we will lose all carbon gain. Let's move to the last set of applications to better understand the urban climate. We need to understand the energy partitioning to explain climatological phenomena such as the urban canopy heat island, which in Mexico City is a nocturnal phenomenon reaching values of 3 to 5 degrees Celsius just before sunrise. But please look careful during daytime. We don't have the heat island effect. We have the opposite. The urban fabric acts as a cooler. It keeps cooler the air close to the surface cooler than the air in surrounding rural areas. What is the basis for this particular behavior? Well, looking at the energy balance, we find that the heat stored by the absorbed and stored by the urban surface, buildings, roads, sidewalks, etc., indicated as delta QS in this graphic, is the second largest heat component during daytime. And this prevents that a large fraction of the solar energy to be transferred into sensible heat. As a result, we get cooler temperatures close to the surface. However, the heat absorbed by the surface go back to the atmosphere at night and give place to the urban canopy heat island. But this heat island effect is not too bad in a place like Mexico City, where nights are a little bit chilly. In addition, the release of this heat at night produce enough thermal turbulence to avoid a shallow boundary layer, which avoid that pollutants concentrate close to the surface. This is very important at the beginning of the day when economic activities kick off. Our colleagues in Singapore have used the energy fluxes that we have measured to test and tune up numerical models to evaluate, to investigate the urban heat island, with the finding that current numerical models are still not capable of reproducing sensible and latent heat quite well. Currently, we are participating in Urban Plumber project to evaluate the performance of 30 urban canopy schemes. Our Flux data from Mexico City and Singapore are the only available for tropical cities. The water vapor fluxes can be used to investigate how quickly rainwater evaporates in the urban surface. Similarly, water vapor fluxes can be used to investigate the evapotranspiration process in the urban environment. Not surprisingly, urban vegetation is the main contributor of air humidity in Singapore. Let's close this talk with 3 recommendations. The first recommendation, Flux towers are a team game. The second one, Flux towers are a long-term effort. Accurate, high-quality data take time and money to collect and process. It's like going for fast food or going for a good hamburger and a beer. And finally, Flux towers are one piece of the puzzle. They provide very valuable information to mitigate climate change and mitigate urban warming, as well as to improve air quality management. But they cannot provide all information needed to do so. Thank you. I'm going to stop here. I will be very happy to answer any question. All comments and suggestions will be welcome. Thank you.
Thank you, Eric. We'll take a couple questions. Want to have a question from Eric?
I wonder if you have any thoughts about what kind of neighborhoods in terms of building structures and variations between building structures that might be more suitable for eddy current observations than others.
Yeah, this is very important. The neighborhoods must be relatively homogeneous in terms of buildings, in terms of size, height, we need to have roads all around. That means that traffic must be across the complete neighborhood. And due to these characteristics, residential neighborhoods are those that work better for urban flux towers. Another important point to take care is the building's height. We cannot mount very tall towers above on the roof of tall buildings. So we cannot use eddy covariant flux towers in downtowns because of the impediment of mounting tall structures.
Hello, Rodrigo. Do you have any update about the network of urban flux towers? Like, what are the new discussions? Or is this going to be like a shared database, or how are they organized? Do you know anything about that?
Yes, the International Association of Urban Climatology is running this network, but we don't count with funding. So we are stuck there. In fact, we are only counting, making a database of where we are running flux towers. Actually, I guess there must be around 20 active towers around the world. There are not too many. As part of when we started this project, Urban Plumber, we found that there are no more than 22, 25 databases with at least 1 year of data. We haven't progressed too much. There are issues with plagiarism. There are issues sharing the urban flux data from flux towers. In my case, I have passed through bad experiences since the towers that I have operated are the only in the tropics. Colleagues from some places don't respect the work done by others. So we are in the urban community, we are still a bit reluctant in fully open the data, but that's something that we have to solve and make the data available for the entire community.
Thank you so much, Eric.
Thank you. Bye.
Okay, our last talk is from Sam Sun from Arizona State University.
Good afternoon, everyone. I think now we are finally reached the most important urban flux topic, which is urban flux. Why urban flux is important? Because first, urban area is the most important carbon emission areas. And secondly, urban area is the area where the most people are living. So it's very important for us to have an investigation of the urban flux measurement. And I'm lucky we are finally reached to this one of the most important topic. So because it's very important, so that this DOE has a very special funding. It's called the Urban Integrated Field Laboratory. And for me, we are aware of the program sponsored by the Urban Integrated Field Laboratory. It's called Southwest Integrated Field Laboratory. We call it SWIFO. And our project is mostly focused on the heat wave and also estimation of greenhouse gas. And then we are also care about air pollutions. And for me, I'm a member of this observation team, and I'm mostly focusing on this net atmosphere exchange measurement. And specifically, I'm using eddy covariance for the urban area at greenhouse gas estimation. And we all know that that eddy flux measurement is a very very direct, efficient, powerful measurement, field measurement for the flux budget, but it's has disadvantages, and especially for the urban areas, because we have very deep at the surface. We have very deep urban roughness layer, and this will cause a lot of issues for the if we want to get a very accurate estimation of greenhouse gas budgets, and so that you can hear, it's very easy to find a height for the low canopy at first, but for the urban areas, we have very complicated buildings, traffic flows, and also people are just moving around, so that we are trying to catch those signals. It's quite difficult, and those are the disadvantage for the urban anti-covariance flux measurement. For us, okay, good. Yeah, for us, we are planning to build 3 to 4 flux sites in the Phoenix area, and so now we only have one site, but I hope I can also but we will have new sites, and I hope I can just present those flux data from our new sites next year here. Okay, so here I'm going to show you one site which has been almost 10 years. It's called AmeriFlux site. It's within a low rise and residential area. So it's like this. So you can see that we have a cassette, and we have Leica 75-500, and the height is about 26 meters high, and you can see it's within and we are in grasses, and we are really care about those. Those are our very valuable possessions, and we assume them are our pets. So when it become dry, we carefully watering them. So then you will see the that we have okay, yeah, here so here I just mentioned that this site is within this local within this low rise at the residential area, but we plan to build a few more sites within other local climate zones. So we will have a very good estimation of several different type of local climate zone within Phoenix, and we hope to get a very comprehensive view about how the greenhouse gas estimation from the whole Phoenix. As you know, that Phoenix is a very dry place, and now we are undergoing drought for almost 20 years. So that here, as you can see, at the drought is especially severe in the 2012, at 28, at the later half of 2020, and also 2021. As you can see here, so it's very obvious that we have very strong sensible heat and a very low observation of latent heat, because it's quite dry, and so the most energy will be consumed by sensible heat. sensible heat is the heat. Sensible. Sensible means we can feel it. That's why Phoenix is so hot, because of sensible heat. We can feel it. Okay, so now you can see that this is the ET flux. And because we have some plants, they are our pets, so we we will just watering it when it is dry. So here we don't see many bigger difference between between the year. But if we show the drought years at 2012, at 28, at 20 at 21, so you can see that the ET flux is a little bit low, especially in the April, May. So we can see that some plants are watered, but maybe some are not. So they have drought stress, so that the ET flux will drop down a little bit. Okay, so now I think you are more interested about CO2 flux. So now we can have a look of those diurnal pattern of CO2 flux. Here you can see that the signal is a little bit noisy, but you can observe something different. One is that during the morning around 8 a.m., you can see there's a peak. This is probably caused by traffic during rush hours, and then it can drop down a little bit because of plant, and then and in the afternoon you can also see there's some peak, and those are also probably caused by traffic. So here we can see that we can observe there is a very unique diurnal pattern for the urban CO2 flux from this low rise at residential community. And this pattern is totally different from our natural ecosystem like farmland, grassland, all those things. So here, this is the unique feature of the urban additive flux measurement we have. And here you can also see that mostly it's carbon source, and we only become carbon sink during July and June at middle day at August. But most of the time it's the carbon source, and we have this very unique diurnal pattern, but this pattern will soon disappear. Be cautious. Okay, so here we can see that in the dry years, you can see that some we can see that this carbon flux can be a little bit low. I think here, and we want to see that in the dry years, that it's more obvious to have a carbon source, and it's most of the time it's the source for the carbon during the dry years. And how about at 2020 during the COVID pandemic? So you can see here that in the April, because of pandemic shutdown, so you can see that the CO2 flux in the morning gradually dropped down, because many people living in home and they don't go to office. So that here you can see that our flux environment catch this dropped down carbon flux during pandemic shutdown. One more thing is about weekdays, so that you can see that during weekend we also observed a little bit low peak in the morning because people don't don't go to office, so that we will have a little bit low traffic, and then the peak in the morning gradually dropped down a little bit. So all those are the unique feature we don't observe from our natural ecosystem, and this is the only unique for the urban advanced environment. As I just mentioned, our very unique diurnal pattern just disappeared if we have the daily interval estimation. So here you can see we have a very good seasonal pattern of temperature ET, but the CO2 flux just disappeared. So now we have a very boring, consistent at the carbon source, but there's no pattern there. So I guess no pattern is also one pattern, right? So here, yeah. So you can see here, and one more thing here is I did the average for each year because we have about 10 years data. So now we can have a clear view about annual pattern or about the seasonal pattern within each year. So you can see that it's quite clear for the temperature, for the ET, but the CO2 flux just disappeared, and we have a very consistent carbon source. So I feel that this is probably also unique for the urban and convergence environment, because we can observe very clear diurnal pattern, but it disappeared for the daily at the seasonal time level. So I guess we need to care about how we will analyze those urban flux measurement, because sometimes the source at the sink will even out if we have a different time interval. So how to deal with this time interval is also very maybe very unique for the urban and convergence environment. Okay, this is my take home message. One is that urban flux is very important, but it's challenging because of we have very complicated urban land cover, and then we need to care about our time interval, and then also we don't observe seasonal pattern, but we observe very good diurnal pattern. At the end, I want to share a little bit about my personal motto. So sometimes when I too much focus on the flux measurement, my mind also has a lot of added turbulence, and I'm trying to just calm down. So I told myself, calm down, and you will have inner peace and power. So I also hope when you are finished your last work, just calm down and may the power be with you. Thank you.
Great. Thank you, Sam.
And it's may the force be with you. Yes.
That's okay. We get it. Okay, any questions for Sam?
Well, I have a bunch, but I'll try to keep it short. One quick question. So with urban systems, the land curve and the land use is kind of complex and a problem. And I'm wondering, in the Phoenix area, how are you guys taking into account the fact that in dry lands, socioeconomics actually really play a big role on neighborhood development? So if you are in an old neighborhood that is a wealthy neighborhood, your canopy cover will be significantly greater than if you are in a newer neighborhood or a poor neighborhood. So I'm wondering, how do you guys take that into account, especially because Phoenix has some old wealthy neighborhoods and a whole lot of exurban development. So how do you take that into account, and what do you think that would do to some of your fluxes? So that's one question.
Sure. Yeah. So because Phoenix is also a very big city, even it's dry at the heart, but a lot of people just moving in. I really don't understand why they come, but they just come. So here we are really, so we will focus on the local climate zone. So we will find a few very representative local climate zone within Phoenix, and then we will do this urban flux observation based on the local climate zone. And and one thing is that it's very difficult to find land and to find a site, and it's very complicated, the permitting process. And there's no optimized method. So sometimes we need to peacefully accept we might to do some compromise, and we can't build a plus tower at the site we want, but we will try our best to a little bit close. Yeah. Yes, that's my question. Yes, question again.
I was talking to you before, and you were talking about you guys are aiming to install more towers. So if you could talk a little bit more about your future project.
Sure, I have some slides here. I just hide them. Yeah. So here we are. Let me see. Yeah, so we are trying to. We have a map for the local climate zone, and then we want to planning to build a few sites for the one is on the and also the desert botanical garden, and we also plan to build a site with a very heavy at industrial area, so that those are our planning. And when I just finish this talk, I will just rush to the Phoenix and to just begin to construct it. So I hope I can present Flux data from those sites next year. Yeah.
Very nice talk. You mentioned a lot of differences between natural ecosystems and urban environment and time scales. So when you look at the daily and seasonal time scales, you get totally different patterns. I actually have two questions. So you mentioned there's watering in
irrigation system.
Irrigation.
Outdoor water use, because those are our pets. They are so cute.
Okay,
yeah.
So would you say most of the source of water in the evapotranspiration comes from watering? So if people, let's say there's just so much demand for water for different purposes, people want to conserve water and they stop watering, would you still see similar patterns in terms of the water vapor flux dynamics?
Yeah, I guess for this is a very challenging, because we need to have an estimation of how many water used for the outdoor water use, and that's a very difficult number to get. So so far I don't have a solution, but I guess I don't know, maybe we can use some soil moisture sensor to get the estimation of the volume of outdoor water irrigation use. I don't know. Yeah, yeah. I think that's a very helpful question, and it's really helpful to get an estimation of ET. But that's also very unique for the urban area, and it's not easy to find at how many percent of water they used for the drinking and how many used for the watering those plants. So it's difficult to partitioning.
Okay,
Yeah,
thank you.
yeah.
Another question I have, obviously, in an urban environment, the relationship between water flux and CO2 flux totally change. I wonder, let's assume you have very little soil evaporation, but most of the ET comes from transpiration. I wonder if it is possible to use the decoupling between ET dynamics and CO2 flux dynamics to decompose the observed CO2 fluxes into natural contributions from let's say from cars.
Yeah,
I mean, you could use carbon isotopes.
Yeah,
but I
yeah.
wonder if there's a cheaper method to do that.
One way is that we can have a camera and to count the cars each day, and then we can get an estimation of this. So now we are planning to have a camera, and then we use some AI method to count how many cars go around each day, and we are thinking about this. But so far, that's yeah, at the mostly maybe at the maybe for the carbon isotope measurement, or for the ET partitioning ways, but that's also now beyond our budget, and we don't have planning for now. And I hope we can find some other fundings, and maybe from at DOE, or maybe here somebody want to sponsor us. Just kidding. So that we can have some other sensors to get a complete picture of those carbon flux estimations. Yeah.
Okay, great. Thank you so much. And thank you all the speakers in this session.
Great. So now we're going to have a quick brainstorming event about urban fluxes led by Dan.
Hey everyone, Dan Rasciuto from Oak Ridge National Lab, and going to talk a little bit about or just brainstorming on urban fluxes. So we heard a couple of really nice talks, and I think already started some good discussion that I don't want to derail too much, but I did want to show a slide on the urban integrated field labs. I can do this. So yeah, we already heard a little bit about one of these. And so this is just from the project, a website, and there are 4 of these sites, and I won't read the whole mission statement, but they're really aimed or geared towards informing equitable climate and energy solutions that can help us strengthen community scale resilience across these urban landscapes. And so the one I'm involved in is BSEC, that's the Baltimore Socio-Environmental Collaborative. There's another in Southeast Texas focused on the Beaumont, Port Arthur regions, and then a third one in Chicago. And I put the logo there to remind myself what the acronym stands for. So it's Community Research on Climate and Urban Science. and then the Southwest Integrated Field Laboratory, spanning several cities across Arizona, including Phoenix. So these projects were funded about a year ago in September 2022. I think the Southwest IFL was funded just a little bit later than that, but these are large multi-institutional 5-year projects. I think BSAC has 9 institutions. They all have quite a few, including national labs, universities, and all of them include at least one minority serving institution or HBCU. They all involve combinations of measurements and modeling, which of course we refer to as MODEX. And so those observations include quite a number of different types, including of course eddy covariance, also looking at soil chambers, plant physiology measurements, data from buildings, energy use or construction materials and things like that. Atmospheric observations, including local conditions, looking at microclimates, looking at air pollution in some cases, hydrology, looking at flooding, and 3 of these are sort of coastal systems. And then the modeling landscape in these IFLs is pretty complex. Of course, there's no one model that can really represent these urban systems. And so we all have combinations of atmospheric models. A number of these projects using WRF for various flavors of WRF, and the urban canopy model, land surface models. And so we're trying to bring in information from ELM, DOE's model, hydrology models, and also very important socioeconomic and decision science models. And so the first PI meeting for all of these IFLs together was last week. So they're all talking about ways they coordinate, keep the communication going. And then next month is a workshop on urban fluxes, which was in the planning stages right now. So as someone who's attending all 3 meetings, this one, that one, and the upcoming one, so I'm going to try to help facilitate communication among these groups. And also here right now. And so I just put up next slide in advance. Oh, okay. And why won't it? Okay. Just some ideas, but feel free to bring up any sort of challenges, gaps, opportunities you feel are important in these types of urban systems.
Just one quick comment also to emphasize how this investment by DOE is important. There's also an ARM campaign. ARM is the Atmospheric Radiation Measurement Program that is planning a Courage campaign, which is at the interface of coastal, urban. It's going to happen December 2024 to, I believe, December 2025, led by Ken Davis at Penn State. I mean, there's a huge investment made by DOE on those urban ecosystems. So.
Yes, we're very excited about that as well. I don't know all the details on the deployment, but it'll be a very valuable source of information.
So kind of since both of you are here, why not putting Stefan on the spot? And do you think your tool can solve their heterogeneous landscape problem?
Thank you. Yeah, great question. Thank you. And Sebastian and I have been in touch on that actually a little bit. So we've done it in the past from a fairly tall tower, 180 meters, I think, in London, that is published. Separated that out into the different emission and sequestration system, parks, industry, and so forth. We're also currently working on Mumbai data as well as Beijing. So I think this could be an excellent fit to help. And just to follow up with a question here, in terms of fluxes, what's your focus here? Is it more air pollution, so NOx, NOx, ozone? Is it more carbon cycling? Is it all of the above? Is it heat island?
I think if you're considering all 4 of these projects, they have slightly different needs, and I think all of those areas are covered in one way or another. Now, myself, I'm a vegetation modeler, primarily working with ELM, and so we're excited about using both eddy covariance data and some of the physiology measurements and soil data to try to parameterize urban plant functional types.
Cool. I was going to mention an opportunity kind of thing as you were showing the urban field sites. Like, so I work for the USDA Forest Service Research and Development, and we have a pretty new program in the last few years, urban field stations that we do. And so some of them, like you're showing, we have a Baltimore field station, Chicago, and I saw one that said Springfield, and I wondered which one it was, and it was Springfield, Massachusetts. So there's one around here. But I'm from Colorado, and we have a Denver urban field station, and I've gotten pulled into that. It's interesting because as part of our Denver urban field station, we're going to start the Flux Tower in Fort Collins to give that on the ground results. But it's a collaboration of a lot of USGS people. For us, we have a lot of University of CU Denver. They're there. It's also a nexus of like social science and a lot of like hydrologists and economists that are interested in water use. It's an interesting because there's a lot of things that I didn't understand or appreciate how it can work with Fluxes. They did a lot of work this summer in like bus stops and like thermal comfort in bus stops. So we actually built a roving portable like Flux Tower station that's based on a push cart, like a fuel chariot you'd put kids in, but we took the kid cart out and put a gill anemometer on it. But anyway, I just want to let I feel like it's the Venn diagram. I kind of represent the Forest Services network of like a lot of social and economic science and some physiology, but not as much, but they'd like to do more. And then what you're considering here, there's a good overlap, and a lot of these places literally have the same focal point for both organizations. So just wanted to throw that out there.
Awesome.
I don't know if this is something you've already thought about doing or already doing, but have you considered adding Flux Towers in like green cities to see how that compares to what we've already got going on? Does that make sense?
And that's a question for the room, not just for Dan. I'm going to translate that.
I know, I think in Baltimore, so the plan is to try to understand at least differences in vegetation densities of the two towers. I know that's not answering the question directly, but we're looking at those impacts with the two different sites.
I'm curious, so there's ICOS cities in Europe. Is there communication ongoing? How is the integration there? I've been involved in a flux processor intercomparison to work towards mapping fluxes in the ICOS, like it's a dozen, I think, ICOS urban sites. So I'm curious, to which extent are you already collaborating?
We're just starting to talk about it.
Mike, but I wanted to. Okay, hi, thank you. I had two comments. One was just a clarification in case it wasn't clear. The urban workshop that's next month is AmeriFlux hosted, but all of the IFL teams are invited. But don't think that you have to be part of an IFL team to participate. It's a AmeriFlux hosted event, so it's open, just to make sure. And then I just have a thought that urban environments are, well, they're called that because people live there. So we're going and working in other people's neighborhoods. So we heard a really neat talk from Clarissa at Harvard Forest yesterday about that. And I just sort of wanted to raise that as when you think about maybe what your scientific questions are, and how you're choosing your neighborhoods and how you want to interpret data and who does it, and especially your questions, I think. Thinking about this is a place people live. Who are they? What are they doing? Might be a good thing. And also, I think sometimes the safety and social preparation questions are a little bit different. There's just some thoughts.
So as messy and complex and challenging as urban systems can be, I think that one of the really big benefits is that you have people there. And there's nothing quite like getting people involved in your own research. And I think that would be a really great opportunity for something like AmeriFlux to tap into the outreach I built my local meteoric water line with people collecting rainfall samples in their backyard. And then they'd text me and I'd come grab their samples the next day. And so I think that it's a really beautiful opportunity for citizen science research, and it can provide such rich data sets. So we're talking about the ecology questions yesterday and what we desire. And like, this is where people can produce your insect data, can produce your transects. They can send you pictures of the vegetation in the backyard, and you can get an inventory of how much native vegetation you have versus non-native, because that's going to impact your ET demand and your water usage. You can, municipalities do LiDAR flights, and you could pick out a pool by the absence of LiDAR data. So urban ecosystems are super complex and messy, but they're also very rich in resources for creating really powerful data sets.
I've done a little bit of urban climate work, mostly on the urban heat island effect, and I'm curious, I guess to that exact point, are you collecting citizen science data actively? I used some weather underground stations, which were littered all around the city that I was studying, and oftentimes they can have really great coverage, even if the sensor, if the data quality isn't perfect. Oftentimes they make up for that with distribution area, and I don't know if that's already sort of like integrated within your study sites within the cities you work on.
Yeah, I know that's true. In Baltimore, we're using a lot of local weather station data. Don't know details about the other projects, but certainly something that's extremely valuable to these projects.
I don't know if this is going to be a question so much as I'm the oddball in my group that I study ecosystem stuff, but most of my lab group actually studies urban greenhouse gases, and there's a few cities that are targeted with these high resolution emissions maps, like Hestia, I think, is one out of northern Arizona. And there's a few cities with really dense urban CO2 and some methane measurements that are not eddy covariance, but just like mole fraction observations. But I think maybe on like a broader city scale, there's been a lot of work done paired with atmospheric transport models to try to map out and optimize emissions over cities. And there's another like vegetation product that uses SIF that someone in our group helped develop for urban environments. And so I kind of wonder if there's opportunities to pair what's going on in those kind of intensively researched city environments from those networks where you can find overlaps in what you learn from these cities. That's it.
Yeah.
Oh, cool. Yeah, sorry. I was looking at you.
Folks online too. I don't know if we want to.
We have a question from Eric in the Zoom room. We're going to unmute him so that everyone can hear. So just give us 1 second.
Yes, can you hear me? I'm there.
Yes, go ahead.
Okay, it's about how to involve people when running an urban flux tower. In addition to the micrometeorological measurements, we have to do also a lot of work on the ground to understand to be able to explain the flux's origin. We need to collect data from neighbors, from people. We need to understand their daily activities, their behaviors. And there is nothing better than talk with people, spend hours on the ground, knocking doors, asking help to collect data about their trees, their gardens, their backyards, how much gas they consume. I don't know. There are many ways to involve the community in this type of studies. That is it.
Oh. Can I add a little comment? Yeah. Actually, I'm a PhD student working on the terrestrial ecosystem, but I have little background about urban water body, because like one of the characteristics of urban ecosystem is a heterogeneity. And of course, most of the cities have a river or lakes or reservoirs nearby. And I figure out the wastewater treatment plants kind of things, like anthropogenic source of the liver, especially in the drought or climate change, this kind of era is the source of like methane or nitrous oxide heavily. So I'm just like wondering, anybody works on the waters, livers, or have you ever any plan to include that on this kind of project?
Yeah, something that I found was interesting that I didn't know before starting, working in these systems was the vegetation sometimes can have its roots in the sewer system, or it's getting water from sources that we wouldn't, our models aren't considering, and that may be a very important source of water to the atmosphere and to the vegetation.
To answer your question about working on water bodies and non-point source pollution, every single municipality has to have a federal permit for discharge waters. And so those data are actually curated and kept by the city, and they're like in Tucson, their auto samplers are hardwired to the power grid. It's like beautiful data. So if you can make friends with the city hydrologist or the person in charge of the permitting, they'll share their data with you and you can start analyzing it and incorporate it. So that, work with your local municipality, with your PIMA and with your local county, because they actually have to produce a whole bunch of data just for permitting. So that's like a totally on tap source of information.
Okay.
Any other
thoughts?
I think this might be boring, but the principles, theories behind eddy currents method comes from our measurements, understandings of natural ecosystems where you have porous, media, and the dimension of objects that can block flow is much smaller than the observational footprint, but that might not be the case in the urban environment. So don't forget to revisit the theories, principles behind the eddy currents method to see if they are applicable to urban environments.
So before I did eddy covariance work, I did a lot of remote sensing work in urban areas, and just thinking about some of the challenges and seeing your slide about different sorts of sources for carbon and things like that. Are there considerations for pairing flux towers with smaller scale like turfgrass towers, and also like tree sap flow measurements to try and isolate what the vegetation itself is doing, and perhaps upscaling with high-res remote sensing imagery and things like that?
Yeah, I think that'll be a really key part of the work. I know in Baltimore, at least, we're doing or will be doing sap flow measurements. Yeah, and combining that with really high resolution remote sensing land cover information to try to understand how the different land cover types are influencing the fluxes.
Thank you.
One more.
Also, the measurements for atmospheric boundary layer, it could be very useful. Yeah, because we see the strong diurnal pattern of them, and yeah, they can be critical for people's health. Yeah, maybe just think about that in the plan.
Yeah, thanks. Wrap up. All right, well, thanks everyone. This was great, a great session, and yeah, we'll take a lot of these ideas, I think, to next month's workshop. Hopefully, have a lot more cool information from these urban systems next year.
Oh, you're stuck with me. I don't know where Christine is. She knows all. But we are now, in a minute, going to move to the poster session. So they are busy setting up easels. And so if you are presenting a poster, please go soon. Right, Christine? Now's the time. Set up your poster. Sorry, wait, sorry. One announcement that I forgot, but luckily he's coming up and I don't know who has that. Christine, you have that slide. Sorry. Yeah, so I'll just say, then we'll have the poster session. During the poster session, the AMP team will have a little table to talk to you if you have questions or you need help with data or tech. Just find them. You probably know who we are by now, but they'll be sitting together, a couple people. And Gil's going to make a quick announcement about another workshop because he won't be here tomorrow. Tomorrow we have time on the agenda for community announcements. So if you have others, that's great. Write them down and bring them tomorrow morning.
I'll just go ahead and say it. So November 15, 16 is the ESS Dive team meeting. It's online meeting. You can go to the ESS Dive website and dig out the link. Will pop up there soon, but you can dig out the meeting sign-up sheet. Again, ESS Dive is a fantastic database. It's a really nice resource. I use it in my group. If you have DOE funding, it's usually a requirement that you post your data in ESS Dive. One thing that we've established works very well is in the site description of ESS Dive. So for example, if you have chamber measurement, leaf measurement, other ancillary data to things that going on in your Flux site, makes a lot of sense in your Flux site metadata to link the DOI of your other ancillary data in ESS Dive. In ESS Dive, in the site description, you can give the DOI of your Flux data in AmeriFlux. Both things can work together, will be cross-operable. But to learn more on ESS Dive, or if you're already contributing there, go participate in the team meeting mid-November.
Yeah, so obviously that's a virtual workshop to make it easy for you to attend. So now we're going to close the session unless there's any other urgent announcements, and we'll say goodbye to our Zoom partners. It's been great to be in the meeting together. And thank you very much for this fantastic session on these challenges and fluxes, I thought. So thanks, Patty. Also, and all the speakers. Okay.